Okay, folks, I've had a lot of you ask me about this question, and we'll go over one similar to it in class tomorrow, but we're looking to find a power series solution to y prime equals xy. So the first thing we're going to do is let's go ahead and put this in standard form. We get this. Then we suppose that there's a power series solution to this, so let's suppose y equals the sum from n equals 0 to infinity of some Cn that's yet to be determined times x to the n. So the way I think about this is sort of like our method of undetermined coefficients. We're going to posit the form of this equation and then go ahead and substitute it in and then find the coefficients that Cn needs to be in order to make it true. So this is what we're going to work on as our solution. To plug it into the equation, we have both y's, but we also have y prime. So let's go ahead and find y prime. Y prime is equal to the sum from n equals 1 to infinity of, using my power rule, Cn times n times x to the n minus 1. Okay, folks, as a reminder, the index started actually at 0, but if I plug in 0 for that first term, I get a first term of 0. So I went ahead and just dropped off the first term and then shifted the index up to 1. The fact that I've got n x to the n minus 1 is just the power rule applied to each of the terms of this infinite series, which it turns out we can do. So let's now plug both of these expressions, y and y prime, into the original differential equation. So we get the sum from n equals 1 to infinity of Cn times n x to the n minus 1 minus x times the sum from n equals 0 to infinity of Cn x to the n, and this needs to equal 0. Okay, so before I get started trying to set these two, or trying to combine these two series, let's first, we're going to do this a few more times, let's first pass this x right here inside the infinite sum. So it's the infinite polynomial, and we bring in this factor of x, so each term in the polynomial gets multiplied by a factor of x, which means that the net result here is we have Cn x to the n plus 1 is to equal 0. Okay. So the next thing I want to do is I want to combine these two power series into a single power series so I can use something called the identity property. Well, for me to be able to do that, I need to make sure that, first of all, these two series start out with the same powers of x. That'll enable me to combine like terms. Notice that if I plug in a 1 into this first expression here, I'd have x to the 1 minus 1, or the first term of the first series has an x to the 0 in it. Whereas if I plug in n equals 0 into the series here, so if when we look at n equals 0, the first term of the series would be x to the 0 plus 1, or x to the first. So these two don't yet agree with each other. So what I'd like to do is let's go ahead and pull off the first term of this series. So we would have, when n is equal to 1, we've got c1 times x to the 1 minus 1 plus all of the other terms in this first series. Let me actually do this in blue just so we can make sure we see. So I'm going to rewrite this as the first term plus the remainder terms. So we've got c1 times x to the 1 minus 1 plus all the other terms in the series. Ooh, that's an ugly sum. Let's clean that up. Plus the sum from n equals 2 to infinity of Cn times n x to the n minus 1 minus the second series. Okay, so cleaning up this first term here, first of all, we just have c1, because this is x to the 0 times 1. And now we do have that both of these series will start off with a first term of x to the first power, which is what we were hoping for. Still, though, before I can go ahead and combine them as a single series, I need to go ahead now and align the indices. It's important that you do it in those steps. I find that it works best. So first make sure they first start off with the same terms in the series, and then worry about aligning the indices. There's probably other ways you could do it, but this is the way our text recommends, and I think it's the right move. So now I want to have both of these series. Usually I want to have them both start at 0, whatever they're currently starting at. So for this one, I'm just going to go ahead and let k equal n. So I'm not going to actually change anything in this series. So we'll just relabel the variable as k. So we get ck x to the k plus 1. However, over here for this series, I'm going to let me do that in a different color. I'm going to go ahead and let k equal n minus 2. And so then if I go ahead and solve that expression, that's when I shift this down, when n is 2, k will be 0, so that's what I want. But if I solve this expression now for n, we get that k plus 2 is equal to n. So keeping that in mind, we can now adjust the indices. So instead of starting at n equals 2, well, when n is 2, we get that k is equal to 0. So we get the sum from k equals 0, still to arbitrarily large number of terms. And then here I'll write c of, instead of n, I'm going to put k plus 2 times k plus 2 times x to the, so when I let n be k plus 2, then n minus 1 would be k plus 1. Notice now these signs align, and it's very easy to see that each of these terms match in terms of the powers of x. So that's a little bit tricky, that relabeling of the series. That's definitely going to be one of the more difficult steps in these procedures. Okay, now we can go ahead and combine this power series, these two power series, as a single power series by remembering that they're both polynomials, and when I add two polynomials together, I simply combine the like terms. Well, the like terms are those with the same powers of x. So the like terms then will be, or the coefficient then will end up being c of k plus 2 times k plus 2 minus c of k, all of that, times x to the k plus 1. Okay. So this is interesting. Now we're going to make a position argument, and if you'd like, I'll go ahead and put a plus 0 here. It might help with that position argument. So the first thing we notice is that C1 needs to equal 0. Okay, I don't think there's any surprise there. C1 has to equal 0 in this case. The next one, this position argument's a little bit strange. I say I've got a polynomial that has it takes on different values for x, but I've got a polynomial, and it's identically 0. Well, the only way that can happen is if all of the coefficients are 0. So then we set ck plus 2 times k plus 2 minus ck. We set that equal to 0. Now let's, so now we've got a way of equating future terms with prior terms. So if I solve this for ck plus 2, I get that ck plus 2 is equal to ck over k plus 2. All right. So I'm going to need this fact, and I'm going to need this fact. Let's go ahead and generate some of these coefficients now. So I don't know what C0 will be, so let's just let C0 equal C0. Then I know that C1 has to equal 0 by what we found up above. And now we're ready to find the next term in the sequence. Well, C2, okay, well in this case, if I look at this side over here, we've got k plus 2. This is the situation where k is equal to 0. Okay? So when k equals 0, we would have C0 over 0 plus 2, or 1/2 C0 is equal to C2. Okay? So then let's look at C3. Well, this is the case where k is equal to 1. Again, because of the way this expression's been set up, we're looking at the k plus 2 term, so C3 would correspond to k being 1. So this is equal to C1 all over 1 plus 2, which is equal to C1 over 3, or 1/3 C1. But what do we know about C1? Get that C1 we know is 0 by that positioning argument. So this is 0. Okay, well, let's keep going. So we've got C4. C4 is equal to C2 over, notice this will always align with the value of the term. So this is C2 over 4, which we could rewrite as 1/4, C2. Well, what is C2? We said that C2 is 1/2 C0, so we get times 1/2 C0. C5, by the argument we just made, is going to always, all the odd terms will be 0. Do you see why? Well, let's just go ahead and confirm that. So this would be C3 over 5, which is 1/5 C3, but we said that's C3 is 0, so we get 1/5 times 0, or 0. Okay, we'll do one more even term and see what's going on. So this C6 will be C4 over 6, which is equal to 1/6 C4, which is equal to, let's see, we said C4 was 1/4 times 1/2 times C0. Okay, folks, there is sort of an art to knowing how much simplifying to do in order to determine your coefficients. Notice I'm not reducing fractions down, I'm not combining them. I like to keep them in this format here. Okay. All right, many of you got to here and then got stuck. So this is what I recommend. Go ahead and now let's forget about the series representation. Well, let's go ahead and forget about the summation representation of y, and let's write out some of the terms. So based on what we see now, we have the first term would be C0, and I'll go ahead and write it as x to the 0, plus C1 x to the 1 plus ... Okay, so then we get y is equal to, well, x to the 0 is just 1, so the first term is C0, plus we know this is 0, because C1 is 0 times x to the first, so that's just 0, plus, and then the coefficient for C2, we said was 1/2 C0, so this is 1/2 C0 x squared, plus the third term we know is 0, since its coefficient is 0, plus 1/4 times 1/2 times C0 x to the 4th, plus 0 for the fifth term, plus 1/6 times 1/4 times 1/2 C0 x to the 6th, plus ... Okay, so I'm beginning to see what's going on here. Notice I can go ahead and drop off all these 0 terms, and I'd like to go ahead and do so. It makes relabeling things a lot easier. So we get y is equal to C0 plus 1/2 C0 x squared, plus 1/4 times 1/2 C0 x to the 4th, plus 1/6 times 1/4 times 1/2 C0 x to the 6th. Now I'm almost ready to come up with a formula for our coefficients. Okay. Well, sometimes it's hard to start recognizing a pattern in the first few terms, so let's go ahead and look at this term right here. By the way, this corresponds, let's go ahead and restart numbering things by n. So this would correspond to the 0th term of the series. This would be the first term of the series. This would be the second. So this is the third term in the series. Okay. So let's see if there's a way we can somehow represent this term of the series knowing that it's the third term. Let's see what we can do. So when n equals 3, we've got the coefficient 1/6 times 1/4 times 1/2 times C0 times x to the 6th. Well, how could we relate these things to both their terms in the series and C0? Let's see here. I'd like to go ahead and rewrite 6 here as 1 over 2 times 3 times 1 over 2 times 2 times 1 over 2 times 1 times C0 times x to the, let's think about 6 as 2 times 3. Okay, so it seems to me that we have 3 factors of 2 in the denominators there. Well, that's convenient because this is the third term, so we could think of this as 1 over 2 cubed. Then we have a 3 times 2 times 1, so that's times 1 over n factorial. Since this is the third term, when n is 3, we have 3, 2, 1. Okay? Times c naught, of course, and then x to the, let's see here, well, we could say this is 2 times 3, and I guess I wasn't consistent, folks, in my numbering. So I'm going to call, if I'm putting 3's here, then that would be 3 factorial. So for n, in the term, we get that it's equal to 1 over 2 to the n times n factorial c naught x to the 2n. So we're almost done. That means that our series solution then is y equals the sum from n equals 0 to infinity of 1 over 2 to the n factorial c naught x to the 2n. But notice that every term in this every term in the series has a factor of c naught. So every term has a factor of c naught, but c naught does not depend on n, so let's pull it out. So we get a solution then of y equals c naught times the sum from n equals 0 to infinity of 1 over 2 to the n factorial x to the 2n. And this is a perfectly good spot, I think, to leave our answer. By the way, I don't think the question asked this, but it could have asked, where is this series good for? Where does it converge to? And we'll talk about that question next time, but you could go ahead and do the ratio test on this one, and we would find that it converges on a radius of infinity. So it's a very good solution to this differential equation. So that's where I'd park it there to answer the question, but let me just make note of one more thing. If I did some more rearranging, and in this case I don't think it's too much of a leap to notice this, I could write this as x over 2 squared to the n over n factorial. Double check me on this. If I distribute this 2 to both the numerator and the denominator, there's a little bit of mistake there. X over 2. Well, I might stop it there if I don't see this mistake. Let's see here. Yeah, I'm not seeing it. I might just stop there, folks. What I want to say is that let's just say it a little. I won't get all the way through it because I haven't thought through this yet. This looks a little bit like our power series for e to the x, but with an x squared term and a somehow dividing by some power of 2. Oh, I think I've got it. So we could write this as the sum from n equals 0 to infinity of x squared over 2 to the n divided by n factorial. Well, now this just looks like our power series solution for e. Remember, e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. And I've made this expression look like this one here up to a substitution. Here, if I were to look at e to the x squared over 2, this would look like the sum from n equals 0 to infinity of x squared over 2 to the n over n factorial, which is our solution. So although we came up with the power series solution, which is what we wanted for this problem, we could also identify it with its equivalent power series representation for e to the x. So what is our solution to this? Our solution is, let's be a little careful there. Our solution is c naught times e to the x squared over 2. And that is the solution to that differential equation, which you would obtain if you used the integrating factor or some other technique. I hope that was helpful.